In this grade 12 chemistry tutorial, I'm going to go over some basic concepts in the mini unit for rate of reaction. And I'm going to do that by looking at this chemical reaction here and this data that was gathered in a trial lab, for example. And then we're going to go over how we find the rate equation, from that how we find the rate constant, and then how to calculate a rate with different concentration. And then finally, I'll show you how to create some sort of proposed mechanism for this reaction. So let's start with the rate equation. To figure out the rate equation, we need to figure out how each concentration, how the concentration for each reactant affects the rate. To do that, you need to see when one concentration is constant. So notice that right here, right, this concentration for this reactant remains constant, whereas this one, if we're going from trial 2 to 4, we double. That's very important, because if we were going from trials 3 to 1, right, it may double, but the concentration for this reactant also doubles. So because not one of them remains constant, you don't know which one actually caused the change in the rate. So that's not going to work out for us. One needs to remain constant. That's your control. Okay, now if this first reactant doubles, notice that the rate also doubles. So you can think of it in terms of like this. So if your concentration doubles and your rate doubles, what would that exponent be? Right? In this case, 1. So we know our rate is going to be equal to our rate constant, and our first reactant, BrO3 ion, is to the exponent 1. Next, if we look at our second reactant, we could do from 3 to 2, trial 3 to 2, as we can see that doubles, or we can go from 3 to 1. The question is, which situation does our first reactant remain constant? And turns out from 3 to 2, it remains constant. So let's look at that. We'll do 3 to 2. We can see that this doubles, and our rate quadruples. So if our concentration doubles and our rate quadruples, what exponent do we need? So we need a 2. So in our rate equation here, we're going to finish it off with HSO3 squared. So there's our rate equation. Next, we can solve for our rate constant using any one of the trials. So we'll just pick a simple one. Right, there we go. We'll use trial 3. So we can plug in our rate. So we have 0.20 millimoles per liter second. And that's going to equal K times our first concentration to the power of 1. So BrO3, we have 2, so 2.0, and it is millimoles per liter to the power of 1, and HSO3 is at 3, so 3.0 millimoles per liter squared. All right, and so then what we get here, let's just leave the left side alone for now. So millimoles per liter second is going to be K. So this is 2 times 3 squared, so 2 times 9, so that's 18. And then our units, so we got millimoles. So we have 1 here and a squared there, so that's going to be, using our exponent laws here, millimoles cubed per liters cubed. Okay, and if we're just looking at units here, we can see how some of them are already going to cancel. So this will cancel with one of those, and this will cancel with one of those. So when we divide both sides by 18, we're going to get K equal to, so 0.2 divided by 18 gives us 0.011. And then when we divide by these units, we are getting liters squared per millimole squared seconds. That's going to be our typical units for this order. So the order of this reaction, we look at our rate and we look at the exponents. So we have 1 plus, and over here 2 equals 3. So the proportionality constant has pretty messed up units, but it's always going to be liters to the power of something over millimoles to the power of something times second. And I usually try to think of it like this. If you know the order, this exponent should be that order subtracted by 1. And that will usually work out. It's a good way to just check. All right, so we figured out our rate equation, our rate constant. Now, since that constant is going to be the same for this reaction, we can determine the rate for these concentrations, right? So it equals K, which we know is 0.011 liters squared per millimole square second, times by our first concentration, 6, so 6 millimole per liter, and our next one, which is HSO3, that is 8 millimole per liter, and that one is squared in our rate equation. So you can see we have millimoles cubed. So 2 of them are going to cancel with this. 2 of the liters are going to cancel with that. And so we get the correct units for our rate, which is millimoles per liter second. And when we multiply those numbers, we get 4.22. All right, next we need to come up with some sort of proposed mechanism. Because you'll notice the rate equation with these exponents do not match these coefficients. So we need to come up with some mechanism. Now, there's really an infinite number of ways you can create a mechanism, but I find the easiest one is to start with the rate equation. So we're going to start with just 1 BrO3, right? Because we just have 1 here, and then 2, so plus 2 HSO3. So there's matching with our rate equation. All right, so let's look at what this can give us. Here we have 2 SO3s. We want SO4s. We want 5 of them. Can we make 5 of them? No, but we can make 2 of them. We have 2 SO4s. And when we do that, we have 1 oxygen left over. That's not what we want, but we have 1 of them left over. We have a bromine left over. And we have 2 hydrogens. We actually want 3 of them, so that one's good. I am happy with those ones. All right. So that one actually matches our rate law. So our second step then, let's just use what we haven't used yet in our reactants. So we need another BrO3. We've used 1, so now we're going to use that second one. We used 2 HSO3s, so we need to use another 3 of them. So another 3 HSO3. This is something we wanted in our reactants, but the O and the Br were not. So let's reuse those. And the 2 hydrogen ions, we wanted those. All right, so now we have a Br and a Br. That's going to get our Br2, which is something we wanted. Now we wanted 5 SO4s, and we've made 2 of them. Can we make another 3? Indeed we can. We can. So plus another 3 SO4. Now when we use 12 oxygens, how many do we have left? So here we have 9, 12, and 13. So we still have 1 left, but we also have 3 hydrogens. So we could use 2 of them with an oxygen to make our water. So H2O, I'm just running out of room here. And then we have 1 more left over, plus H. Well, that's great, right? Because there's our Br2. So we've got 1 of those. We made 3 and 2, so we made 5 SO4s. We've got 1 water, and then we wanted 3 hydrogen ions, so 2 and 3. Now, because the first step matches our rate law, that's our slow reaction, and the other one is our fast reaction. So you can see very easily this is a complicated equation, but we only did it in 2 steps because we just made sure our first step matched the rate law. And the second step, we just used whatever was left over. So I hope that helps. If you have any questions, you can let me know in the comments. And if you have a quiz on this at some point, good luck.